All right, so let's get started with the second part of the tutorial. Welcome, everyone. Welcome to all of you who are joining now. I'm going to be walking you through most of part 2 of the tutorial. Then Scott is going to take over at the very end to talk about future research directions and some applications. What I'm going to focus on is basically a mechanism design approach to this problem. Okay, so far we have focused on Mohammed and Scott. Focus on conceptual issues. How do we design a market when we care about inequality? The way we think about inequality is that because of some underlying wealth inequality, other types of inequality, the designer doesn't value giving $1 to each agent the same. She actually values it differently based on these welfare weights lambda. We thought about how to choose the optimal price in the market, maybe 2 prices, when this objective function of the designer includes these welfare weights, includes this redistributive motive. Okay. But now we would like to understand this problem a little bit more generally, without imposing any structure on the types of mechanisms we can use, but in some generality where we can just derive the optimal mechanism overall to just maximize this redistributive objective function. And basically what I'm going to argue in this part of the tutorial is that we can adapt very well-known tools that I think most of you should be familiar with, basically the ironing technique of Myerson 81. To solve for the optimal mechanism when the designer has these redistributive preferences. And so my goal for this part is to go relatively quickly through the framework in a fair amount of generality, but to kind of show the framework's potential to address these issues and illustrate a little bit how the technical side of this works. Again, I'll draw analogies very heavily to Myerson. So I'm kind of presuming that you know Myerson 81. This is of course, the paper where he showed how to solve for the revenue maximizing mechanism and auction. If you don't know Myerson, you should still be able to follow, but you won't necessarily understand all of the technical details. And this part basically builds on Myerson's paper originally, Condorelli's very nice paper from 2013, as well as our own working paper, a recent one. I'm not going to draw a distinction which parts are coming from which paper, but please consult the tutorial website to read more about the individual papers. So here's the framework, and I'm going to be basically extending the framework that Mohammed was using. Okay, we're going to focus on allocating resources to buyers, and of course you can do the same exercise for the sellers. It turns out when you look at general mechanisms, it doesn't really matter which side of the market you're looking at. So just to recap, a designer is allocating unit mass of objects to a unit mass of agents. Here's the first extension. Objects are now going to have qualities. So far we had homogeneous goods. But for practical purposes, like if you're running a housing assistance program, of course, houses have different qualities. Goods in general have different qualities. You want to capture that. And so now objects have qualities. And there's some distribution with CDF of quality. This is what is the pool of objects that the designer has available that she can allocate to these agents. Now, each agent is going to be characterized by a type which has 3 dimensions. And 2 of them are familiar. Is going to be the willingness to pay, which was called the rate of substitution. Now, because we're just looking at buyers, let's just call it willingness to pay for quality. And you've seen the social welfare weight. That's the key ingredient of the model that captures these redistributive preferences. This is how much a designer values giving $1 to an agent. There's a third new element of the type, which is called the label, and denoted I. So this is a very simple idea. Actually, someone asked this in the chat. What if we have access to some additional information? This is freely available to the designer. In the medical context, maybe we have some access to objective data about the patient's health. In other social assistance programs, maybe we have some access to data on incomes that the participants have. What if we can use this available information to design the mechanism as well? Right? So that's the idea of the label. And as was previously the case, we still assume that the distribution of this type is known to the designer, but only the label is directly observable. So the designer can estimate the distribution of willingness to pay and the distribution of welfare weights based on these labels, right? And the utility keeps being very simple in the sense that we're assuming linearity. So if an agent with this 3-dimensional type gets a good with quality Q and pays a price T, her utility is just linear in the quality. So just quality times her willingness to pay minus the transfer, right? So again, you can think of the R willingness to pay as sort of like a value in a standard auction model. But then the contribution of the individual to the social welfare, which is ultimately what the designer is going to maximize in this framework, is lambda times the private utility. So again, you can think of lambda as how much I'm willing, as a designer, how much I'm valuing giving $1 to an agent. This is capturing the inequality in the market. Now, the main generalization relative to what you've seen in the first part is that we're now going to allow for arbitrary mechanisms. And of course, to do that, we're going to apply the revelation principle. So we're going to look at direct mechanisms in which agents report their private information to the designer. And then the designer specifies an allocation and transfers. An allocation here in general, because we have now qualities, is a lottery over qualities. And then there's going to be an associated payment. We'll have the standard constraints. So the feasibility constraint, don't read the math, but it basically is saying that I cannot allocate more objects than I have. What I have is this distribution F of quality. I cannot allocate more quality than I have. Potentially, I can discard some of the qualities, some of the objects. The AC constraint, the standard one, an agent should report her privately observed part of the type truthfully. We don't need to elicit I, the label, because that's by assumption that's observable to the designer. We have the AR constraint. Agents should want to participate in the market. We have one constraint that's not standard, which is the non-negative transfers constraint. This basically is saying at this point, I cannot give agents a lump sum payment in the mechanism. This constraint actually will allow us to be more general with this framework. I'll explain this in a second on the next slide, why this is actually allowing us to be more general. And here's the objective function. The designer is trying to maximize the expectation over the type distribution of the weighted sum of the revenue. This is just the transfer, and there's a weight alpha on revenue, and the sum of agents' utilities weighted by these social welfare weights. Okay. The alpha here, the weight on revenue, is also a new element. It's a kind of a generalization of what Mohammed was presenting. And let me actually explain. Think of market design, we would like to think of more flexible ways to spend that revenue in a redistributive fashion. So we want to think of alpha as capturing the best possible use of revenue for the designer. And here's why we can be more general than that, than the previous framework, because we can, of course, as a special case, set alpha to be equal to the average welfare weight. This lambda bar means average for some label I, okay? And if we set the alpha to be this, then it's as if we were giving a lump sum transfer to agents. So we ruled it out in the mechanism itself, but if we value revenue at alpha equal to the average or the average welfare weight in some group, of course, if we have multiple groups, we can always give it to the group that maximizes that average welfare weight. That's as if we could give them a lump sum payment. If we cannot use the labels to give a lump sum payment, but we can still give a lump sum payment to all the agents, then we can always set alpha to be the average across the entire society, the population, of these average welfare weights. Okay, that's as if we could give a lump sum transfer to all the agents. But because we're flexible about alpha here, we can capture other interesting cases. Alpha could be higher than all the average welfare weights. And that's the case when there is some sort of outside cost. So maybe I gather some revenue in this market that I'm controlling, and then I can build a hospital that is socially even more valuable than giving back the revenue to the agents as a lump sum payment. The most interesting case we can capture, and that one we can capture precisely because we ruled out lump sum payments in the mechanism description, is we could have alpha lower than the average welfare weight. That is capturing a case when I actually cannot give a lump sum payment to the agents. So the marginal value of generating revenue in this mechanism is actually below this hypothetical value of giving lump sum payment. And this could be because I cannot, for political reasons, give a lump sum payment. I cannot give a cash transfer. Or maybe if I'm giving a cash transfer, it's costly. For every dollar I collect, only 90 cents goes back to the agents, and therefore alpha is below the average welfare wage. Okay. So with this framework, we can be kind of flexible about how we spend the revenue gathered in this market design context by setting alpha to one of these possible cases. Okay. Now let's talk a little bit about deriving the optimal mechanism. So this is something that Mohammed has hinted at. Even though agents in this framework have these two-dimensional types, well, they're three-dimensional, but the label we can observe, so that's easy. We can only elicit information about the willingness to pay R. We cannot really hope to elicit and then condition the allocation and transfers on the lambda, the welfare wage. And intuitively, this is the reason for that is that the agent's private utility only depends on R. Okay, so if we try to elicit lambda in the mechanism, agents would always just lie. They would always just report the lambda that gives them the best treatment, and there's no way to incentivize truth-telling of the lambda. So our mechanism will have to depend on labels, which we just freely observe, and that willingness to pay, which we can screen for using prices. So as a result, to understand what mechanism is going to emerge as optimal in this framework, we have to calculate the expected benefit of giving a unit of quality to an agent with label I and willingness to pay R. Okay? And I would like to derive this object for this framework starting from something much simpler that's going to look familiar, just to kind of draw an analogy to something that you have seen before. So here's one special case we could look at. This is kind of the classical setting of a first welfare theorem, or think maybe of allocative efficiency as your goal when utility is perfectly transferable. What's the social value in that canonical framework where you care about allocative efficiency only? What's the social value of giving a good to an agent with willingness to pay R? It's exactly R. The value is the willingness to pay, right? And in this case, it's trivial that you should just use the price mechanism, a market mechanism. Right? Here's a different case you're probably familiar with. If we assume that GI of R is the distribution of willingness to pay. So in Mohammed's talk, the G already appeared. It just was indexed by I because we didn't have labels. Now it depends on the label. If we assume that we have this continuous distribution, we can capture revenue maximization as another special case of a VIR function, right? This is what we were taught by Myers in 81. We just have to set this VIR to the virtual surplus, which is the actual surplus minus the information rents, the inverse hazard rate, and that is going to correspond to maximizing revenue. Okay, and we know from Myerson if this function is increasing, this is the so-called regular case, then again some sort of auction, potentially with a reserve price, is going to maximize the objective. Okay, but let's come back to the case of maximizing some sort of utility of the agents. Notice that with perfectly transferable utility, we can decompose this into this revenue term and the utility of the agents. And what's kind of very stark here about this perfectly transferable utility case is that we simply don't care who ends up with the money in this problem. Does it end up with some agent? Does it end up in the designer's pocket as part of revenue? It's just completely irrelevant. And this changes completely in this redistributive framework because now we put weights on these two terms, right? We put welfare weights on the utilities of agents, and we put the alpha weight on the revenue in the designer's budget. And this is where the richness of the framework is coming from. Okay, what is this welfare weight that we put on the agent's utility? Well, the sort of primitive welfare weight is the lambda, but we don't observe lambda directly. We, as we kind of argued in this lemma, we only observe the label, and we can potentially elicit information about willingness to pay. So what we're going to do is we're basically going to try to estimate these unobserved lambdas based on the things we can observe. Okay, and as Mohammed and Scott emphasized in the first part, we can expect that there will be indeed dependence of the expected lambda on willingness to pay, because higher willingness to pay is most likely associated with people that are richer, and to the extent we care more about poor people, we're going to infer that lambda is going to be decreasing in willingness to pay. Of course, these expected lambdas are also going to depend on labels. If the label tells me you have low income, this expected lambda will be higher. If I tells me you have high income, this will be potentially lower. Okay? So this is how this observable information feeds into the objective function through this expected welfare weight. And that's basically the objective that we want to maximize. Okay? And again, this is the economic idea. We're trying to forecast these welfare weights. Let me skip this part because that's what we covered in detail in the first part of the tutorial. The idea here, even though we're going to treat this from now on as a primitive of the model, this function, is that the shape of this function depends on the market context. This was the example that Scott gave. We probably expect this lambda IR function to be strongly decreasing in willingness to pay if we're talking about a good like a life-saving treatment. But we don't expect a very strong correlation between this willingness to pay and the welfare weights when this is kind of a pretty affordable good that mostly the willingness to pay is going to be driven by differences in taste, not by differences in ability to pay. But this object is going to fundamentally change how we're going to think about choosing a market versus a non-market mechanism. Okay. So now I want to spend a little bit of time talking about techniques. So how to derive the optimal mechanism in this framework. And again, my emphasis here will not be on covering every single technical detail, but to give you kind of an overview of how to think about these methods. And the way I'll try to do this is by drawing an analogy to Myerson again. There's one difference to Myerson, though, which is we have these labels, right? We have these observable pieces of information. And as a result, we're going to solve our problem in 2 steps. We have this pool of quality for everyone. We're going to split it first across the groups. A group is just everyone with the same label. Right? This is a mechanical step, but nevertheless is an important one. We have to split the objects into groups. And then in the second step for each group, now that for every group we have an assigned pool of quality levels, we're going to now solve a standard screening problem based on willingness to pay in that particular group. And the second step is where we're going to borrow from Meyerson. So to make it very clear, there's an analogy, and I'm hoping that this will be illuminating. I'm actually going to briefly recap Meyerson's ironing for you. And one thing I want to say here is that at least the way this is presented in econ programs, we think of ironing as kind of this quirk of the revenue maximizing model that, in a regular case, you don't need to do ironing. But if things are ugly, that's where you have to kind of to roll up your sleeves and do this ironing thing. In contrast, this is going to play absolutely center stage for our framework, which is why I'm really focusing directly on the ironing case here. Okay, so how do we do ironing? A very brief recap. We start, as we said, so for Meyerson's problem, this is just revenue maximization. So we're going to start with virtual surplus as our VR function. Right? We start with virtual surplus. If it's monotone, by the way, there's no need to iron. The interesting case is when this is not monotone. How do we iron the virtual surplus? Well, this is one way to do it. We integrate that function in the quantile space, and I'm sure most of you are familiar with this step. You concavify that function, and you differentiate back. Because the function is now concavified, your derivative is going to be monotone, so you're going to get the ironed virtual surplus, which is going to be a monotone function. You can base your allocation on this ironed virtual surplus. And the recipe is simple. If the ironed virtual surplus is negative, do not allocate in that part of the type space. If it's constant, if it was ironed in some interval, that's when you use randomization, basically, to be more precise, a constant allocation that is not increasing in the reported type. And finally, whenever the iron virtual surplus is increasing, you use some sort of auction to achieve an increasing allocation, that higher types get higher probability of getting the good. That's the idea. And now the magic of Meyerson's ironing is that it really doesn't matter what this VR function is. For Meyerson, it's virtual surplus, but we can put any function we like. And of course, we're going to put in the function from this framework. And we can use the same type of procedure. Now, I do want to say there are a couple of technical details because we have this quality and so on, but it's going to work in exactly the same way conceptually. And one reason for that is, even though we have the quality, because our utility is linear, all that's going to matter is expected quality. So instead of allocation probabilities in this problem, we're going to have expected qualities. Okay? And again, just like in Meyerson's ironing, we're going to have these parts where the allocation is increasing and parts where allocation is constant. We're going to have the precise analog of that, which we're going to call the market allocation and the non-market allocation. What is the market allocation in this framework? Well, it's going to be the assortative matching between willingness to pay and quality, right? So basically, it's an increasing allocation in this model. It's assortative matching, meaning that higher willingness to pay agents are going to get higher quality. And we call this the market allocation because that's what the market would achieve if we just let the market do its own devices, if we let the market set the market clearing price. In contrast, the parts where it's going to be ironing, we're going to call it the non-market allocation because that's where the matching between types and quality is going to be random. So that's some sort of randomization or sort of rationing that we'll need to impose sort of artificially to clear the market. Okay. But basically, we can prove using the same type of sort of ironing procedure that only these things could happen for a given group of agents. And in fact, here's how it works. So I'm going to show you a picture, hoping that this will clarify. This will also actually show you how to solve the across problem, the first step in the procedure. So let me go through this quickly. This is an illustration with 4 groups. So think of 4 labels. I have the quantile space. So I have types on the x-axis in the quantile space, and I have the value generated from allocating to this group on the y-axis. So what I'm going to draw here is this integrated VIR function. So just like in Meyerson, we integrate virtual surplus. Here we're going to integrate our VIR function, which remember is this weighted sum of virtual surplus and the weighted information rents. We're going to get some shape. I just drew some random shapes here for this graph, right? What we're going to do is we're going to concavify these functions. Okay, that's a very simple step. We know how to concavify. In fact, it's the decreasing concave closure, to be precise. And then we can read off the solution straight from this procedure. Whenever the concave closure agrees with the original function, that basically is when VIR is increasing, we're going to get associative matching. In the group 1, for example, we have associative matching everywhere. whenever the function lies below its concave closure, like in group 2 here, we're going to get random matching. Okay? And of course, what groups 3 and 4 illustrate is you can have kind of a hybrid case where for some interval of the type space, here the function is flat, this corresponds to free disposal. Then there's a region of associative matching, a region of random matching, a region of associative matching again. But the principle is the same. Whenever you ironed, you have the random allocation. Whenever you are not ironing, the function coincides with the original function. That's where you have the market allocation, the associative matching. Okay. So that's basically kind of ironing on steroids. The reason why I wanted to show you these graphs is that now I want to argue that once we solve this within group problem, this tells us how to solve the problem of optimal allocation within every group. But we still have to solve the problem of how to split those qualities across the groups. What qualities should group 1, 2, 3, and 4 get? And the nice feature of the framework is that this actually gives us an answer. And the answer comes in the form of a greedy algorithm. Why is it greedy? I think for this crowd, this should be pretty straightforward to see. It's greedy because in the process of solving the within problem, we concavify these functions. We have concave value functions, which means that marginal values are monotone, right? They're monotone, and so we can solve this in a greedy way, starting from the lowest quality to the highest, always allocating to the group of the lowest marginal value, right? Because we're starting from the lowest quality, we're going to ask, where is the lowest marginal value I can get? Of course, we could also start from the highest and ask, where is the highest marginal value? So let's see how this is going to work. This is my quality axis. Okay, I'm going to start with the lowest quality. I'm going to ask myself, which of these 4 groups has the lowest slope? Okay, and the slope here, to be precise, the absolute value of the slope is going to correspond to the marginal value of allocating to this group. And it turns out to be group 3. It actually has 0 slope at the beginning of the allocation process. So I'm going to start allocating the qualities to group 3. At some point, I'm going to hit this part of the graph where this curve is going to start sloping downwards. At this point, the lowest slope is actually going to be not only achieved in group 3, but also in group 1. So in this part of the algorithm, I'm going to kind of allocate both to groups 1 and 3 at the right proportion, so that as I keep allocating, these marginal values stay the same, because I need to always follow the rule. I'm allocating the next unit of quality to the group with the lowest marginal value. Okay, we can just follow this procedure and solve the problem in a greedy way. I hope the principle is relatively clear. So I have some problems with my voice, which is why I'm taking a pause here. But by following this simple procedure, we can basically solve the cross allocation problem. Sorry about that. Okay, I have about a couple of minutes left. So I want to now show you about 2 main economic implications of this general problem. And these 2 implications are going to be basically 2 reasons to use a non-market allocation. And one is going to be a generalization of what Mohammed was talking about. One is going to be novel. So first, let's assume that the designer can give a lump sum transfer. And notice in Mohammed's simple exercise, in fact, this was exactly what the designer was doing. She was spending the excess revenue on a lump sum transfer. Okay. In this framework, it means that the weight on revenue alpha is at least weakly above the average welfare weight, right? One thing I can do with the revenue, its value is at least the value of giving lump sum payment. Then this ironing procedure tells you that you're going to want to use a random allocation, this non-market mechanism, precisely when this objective function in the framework is not increasing everywhere. Right? Whenever it's going to be decreasing in some part, you're going to have some ironing, and this will justify using a non-market mechanism, some randomization. So let's differentiate this function and check when it might fail to be increasing. When is it locally decreasing? And of course, there are lots of terms here, so this could go either way depending on how these terms interact. But the key term to look at is the first one. This is the inverse hazard rate. This is always non-negative, right? In fact, it's positive for most of R. So if this term is sufficiently strongly negative, then we're going to have that the whole expression is negative, and we will want to use some non-market mechanism. And basically, this term being strongly negative is precisely the idea that there is strong negative correlation between willingness to pay and these unobserved social welfare weights. This is saying where this expected welfare weight is going down sufficiently fast with the willingness to pay. if I observe someone with very high willingness to pay, I'm almost sure that they must be very rich. It cannot be that this is just driven by the need, it's just driven by their wealth, and therefore I can conclude, if I have distributive preferences, that they have a low welfare weight, and in this case I want to use this sort of rationing random allocation. This is basically generalizing what Mohammed was talking about. And notice this condition is likely to hold when, first of all, the descendant does have strong redistributive preferences, so there's a lot of dispersion in the lambdas themselves. The good being allocated is relatively expensive, and everyone needs it. This is kind of the best example is, again, this life-saving treatment. And notice the one new element here is that the label I should not be very informative about the lambdas. Okay, that's the new insight coming from the labels. If I is going to be very informative, if the label is going to tell me all I need to know about the welfare weights, the residual correlation with R is going to become very weak. Right? If, for example, I can observe people's exact incomes, if this is what the label tells me, I no longer have to use this imperfect proxy of willingness to pay to infer who's rich and who's poor. And as a result, this function is going to be more or less constant in R. And this inequality is not going to hold. I'm going to use the standard market mechanism to allocate efficiently. Okay. So this is the first reason. That's what basically Mohammed already covered. And this is just a generalization in this framework. But it turns out there's a second distinct reason to use a non-market mechanism, which materializes when you cannot give a lump sum payment to some group I. This is something we can cover because of the labels that we introduced and the assumption that you cannot give a lump sum payment directly in the mechanism. And it turns out that what's important for this result is that the good is universally desired. Here's the definition of this. So basically, what we mean by this definition, by this term, is that everyone has positive willingness to pay. It's in fact bounded away from zero. So this is some sort of essential good, like housing or food, that everyone needs. And so here's the second result. If, in fact, you cannot give a lump sum payment, so the average weight lambda I is strictly larger than the weight of revenue, and the good is universally desired, then you want to allocate the lowest qualities for free in a random fashion, to, by definition of this screening problem, to the agents with the lowest willingness to pay. So under these circumstances, you're basically providing the lowest quality goods for free, using some sort of rationing scheme. Of course, this doesn't rule out the case that you might still be using prices for higher qualities. This is just saying you're allocating the lowest qualities using a lottery for free, but you might still charge prices for those higher qualities. Okay? And notice the intuition here is very different from everything that was happening in the first part, because the only assumption we have made is that the average weight is pretty high in this group. It's above the weight in revenue. So it's not that you're actually giving these goods for free to the agents with low willingness to pay because you care directly about these agents. Rather, the correct intuition is you want to give high utility to all of these agents. And the way you do this is basically you distort the allocation at the bottom to lower prices for everyone. That's fundamentally the reason why you're distorting the allocation for the lowest types. I apologize. My voice is basically breaking down. I'm not sure if you can tell, but I'm kind of struggling to get words out. I apologize. But that's the second reason to use a non-market mechanism in this framework. So let me try to conclude and hand it over to Scott. What we have learned from this part is there are two distinct reasons to use what we now can call in-kind redistribution, this non-market mechanism where you allocate some quality levels at distorted, basically below market clearing prices. And it happens when something you can observe in the market uncovers some underlying inequality in the welfare weights. And there are two sources of this revelation, potentially. There's the label-revealed inequality, when this observable information in the labels is revealing some groups of high welfare weights. And this can kind of provide some qualified support for programs, like housing programs, where you have to satisfy some verifiable eligibility criteria to be a participant. And there is the inequality revealed by the willingness to pay itself. So when the labels are very informative, that's when we use the market behavior itself to identify the agents with potentially the highest welfare weights. And we subsidize these agents by providing the goods at a discounted price. This is roughly how, for example, public healthcare works in European countries, where basically there's typically some sort of private market where prices are higher. There's a public option which is cheaper but it's lower quality. And the fact that you're choosing the lower quality option in the public market is basically identifying you as an individual that's not at least extremely wealthy. And then basically you're being subsidized by having a discounted below market clearing price for these services. Of course, there are still reasons to use the market mechanism. If you care a lot about revenue, when alpha is high, then of course this will be a force in favor of market mechanism. So I focus on the results, talking about non-market mechanisms, because this is sort of new relative to a standard economic intuition, but the standard economic intuition are still here. If you want to maximize revenue, for example, because you're allocating to corporations and you have a much higher value for revenue by using it for some sort of outside cost, then of course this is going to be a force towards using some sort of auction. And of course, the typical efficiency maximization motive is still here. If the welfare weights are not very dispersed, or if you cannot identify the dispersion because willingness to pay is not very informative about the welfare weights, that's when you're also going to use a market mechanism. Okay, I'm going to stop here and hand it over to Scott. Sorry again for the problems with my voice.
All right. First, just quickly, can everyone hear me? Someone give a nod. Okay, cool. Got the thumbs up from Sheng Wu. Awesome. And the yes in the chat from Ishan. Thank you so much. And Piotr, special shout outs for making it through that with the with your voice, just barely holding on for the to the point of the talk. So to wrap up on sort of all of this, I want to take us back to sort of a high level, think a little bit about policy and applications, tell you a little bit about sort of related like models and frameworks that people have worked on so far. And then of course, as important for a tutorial, I'm going to close with a bunch of sort of open questions and challenges and sort of things that people here might think about if they're interested in trying to understand how to redesign marketplaces to try and improve equity. But just very quickly, let me give a high level summary again of what you've seen. So we've been working through a micro market design approach to redistribution using tools from optimal mechanism design. We've been thinking sort of how do you design a single market if you're a designer who controls that market and is concerned about inequality. And again, the high level TLDR takeaway is that it may be worth distorting the market's allocative role in order to make better use of the transfer role. We might want to distort the allocation in order to effect transfers through the market. And this gives a justification for all sorts of, sort of types of distortive market allocation policies that sort of classical economics doesn't usually condone, right? It's, it gives us a reason for in-kind redistribution, gives us a reason for priority-based allocation, price controls, and all of this we think of as really being complementary to public finance, in the sense that, first of all, lots of regulators do control and oversee only a single market, and moreover, there's some friction to tax-based allocation. And then, because I'll show that last bullet point. It's possible sometimes that you might learn things about individuals through their behavior that you couldn't necessarily just see at the central government level. And so again, right, just as Piotr was just highlighting, and as Mohammed set up in the first half, what's really going to matter is sort of the shape of inequality in the market, and then how much agents' behavior reveals about that inequality, right? Like you're only going to want to do redistributive allocation if we're actually able to learn something about the welfare weights from the way agents behave. And then as I hinted, sort of sometimes this is going to give new information, right? And the framework that Piotr just presented really makes that clear, right? There's this concept of a label that's sort of whatever is observable, and then the willingness to pay revealing information on top of that. Lots of things are observable, right? If you're the government, you might be able to see people's income, you might know where they live and so forth. But still, sort of high willingness to pay conditioned on all of that might reveal something about needs. Similarly, on the seller side, you might know somebody's income. High willingness to sell, even conditioned on that, might reveal idiosyncratic cash needs. I spoke about Uber at the very beginning. Lots of people started driving for, or rideshare, not Uber specifically. Lots of people started driving for rideshare companies at the very start of the pandemic, at a time when rideshare sort of became, in a clear but very also uncertain way, much more dangerous to be driving. The inference there is probably that they had an idiosyncratic need, right? Maybe they were just furloughed from their job, or maybe they have a family member who became ill, and so they needed extra money at that exact instant. And while the government did eventually learn, for example, who was furloughed, first of all, the market response is immediate. But second of all, this information, like you have a sick family member, like that's the type of thing that actually like you might only be able to elicit through people's behavior. And so we see this like market-based redistribution as a fundamental complement potentially to macro approaches, rather than just something to do when the macro approach isn't working. Just quickly, this has changed the way we think about lots of different allocation problems. Sort of start of the pandemic, there was a lot of price gouging in hand sanitizer, right? People, went and bought hand sanitizer mostly from places like the dollar store, and then sold it, at 40 to 100x markups on Amazon and other sort of online resellers. And if you think about that in the frame of our model, that's actually an extremely regressive allocation, right? You're taking hand sanitizer from places that are, on average, maybe skew even lower income, but whatever the case, hand sanitizer is sort of like equidistributed across the, sort of stores and population centers. And you're now ensuring that it only goes to people who, have access to the internet and the buying power to buy it at 40 to 100x markups. And key, right, is this idea that willingness to pay convolves your value and your ability to pay. Everyone has high value for hand sanitizer in a pandemic, which means it's mostly about ability to pay. Your ability to pay $40 for a bottle of hand sanitizer doesn't show your level of need. It just shows your level of cash. And moreover, if anything, again, thinking about welfare weights, if you're in the category of people who don't have the ability to pay $40 for a bottle, then you are more likely to be someone who's working in person, who faces higher risk. And so thus, if anything, should have, we care more about allocating the good to. So in all of these dimensions, like the welfare weights are sort of the opposite of what willingness to pay reveals. Whoops, sorry. And something is beeping. That's super interesting. I did not know that device did that. Right. Okay. So that's hand sanitizer. Similarly, in the context of food stamps, and this stuff also plays into questions about inequality on platforms. Lee Jin and others have been writing about, sort of platforms trying to enable creators, creator economy platforms, enabling creators to sort of make enough money to really invest in being a creator as a business. And to do this, you actually have to think very carefully, because this market is by nature one in which it's very sort of tail dominated. So you have to think hard, how do we choose the allocation rule in these types of markets to improve equity among participants? And then lastly, a question we often get is, sort of how does this interact with sort of broader competition, right? In the case of rideshare, for example, would it ever be in a platform's best interest to try and do redistributive allocation? And this is one of many open questions that we don't have a clear answer to, and might be a fun thing for some of you to think about. But it's at least not obvious which way the comparative static goes. And indeed, New York, was one of the earliest places to insist on a rideshare minimum wage, and the long run outcome was, I mentioned earlier, right? Rideshare, low price elasticity, the long run outcome was demand for rideshare didn't change much at all. Earnings of drivers went up. And indeed, in the long run, the platforms also made a little bit more money on the margin. And so it's not totally clear, if you, especially if you're doing something where there might be general equilibrium effects, which of course are entirely outside of our model, if you can sort of improve, socioeconomic equity, then maybe that actually feeds back into the platform ecosystem being stronger in the long run. Okay, there's far more work being done in this space. This list I'm about to give is emphatically not exhaustive, and I'm going to run through it very quickly. As I said, all of these references and many more are on our website. So Kang and Zhang look at a version of this redistributive allocation problem where the buyers and two-sided market with the buyers and sellers sorting endogenously. And they have this very elegant result that shows that, you know, the welfare weight that ends up determining whether you want rationing in this context, when people are sort of deciding whether they're going to be a net buyer or a net seller, think of this as like a property right that we've allocated to everyone, and then they can trade around. You know, the thing that matters is sort of whether the types near the cutoff, you know, sort of have high welfare weight or not. Kang, this is a different Kang, you know, has a model in sort of public goods allocation in the presence of a private good as well. And the key dynamic there is that the availability of the public good affects who buys the private good. And just as Piotr was saying at the end of his segment, you know, the sorting, right, who selects into the public option ends up, you know, sort of impacting the, you know, sort of determining the welfare impact. And what Kang shows is that the public option does indeed end up being rationed in the optimal allocation. And also, interestingly, the value that public option creates ends up sort of going to the middle of the wealth or inequality distribution rather than the poorest agents. Kang also has a paper on externalities. Here I've quoted directly from the paper because it's you know, the point is so crisp. Just like we talk here about the correlation between the correlation between the, you know, revealed type and the welfare weights, so like your willingness to pay and welfare weights, you can do a similar sort of exercise when thinking about markets with externalities, unobservable externalities, because the welfare weight, you know, could incorporate the externality as a term. And here again, it's like if there are a correlation between the individual's consumption behavior and the amount of externality generated, you can exploit that in the optimal allocation rule, just like in our context, right? You're saying it's essentially the same sort of, you know, underlying dynamic that we can use people's behavior to infer what their average externality is likely to be. And again, that all goes into this sort of like, you know, weighted welfare function. Also, Alan and Rebek, apologies, I actually don't know how to pronounce the latter's last name, you know, started looking at an empirical framework to try and understand like what you need to achieve joint identification of a value for good and the value for a good and a value for money. Then, and I've separated by sort of a gap here, there are a number of other different ways in which you could think about adapting the, you know, sort of how you model inequality in the population, right? We've done it in this sort of like, you know, general welfare weight on the, you know, the transfer, right? Like the marginal social value of allocating $1 to an individual. You can also think about inequality as modeled through budget constraints, right? People have different abilities to buy in the market as modeled by their maximum total spend. You could be different bargaining power, could be different, like, you know, sort of costs of waiting or something of the sort. In all of these contexts, this key idea that you can infer things about, you know, sort of people's welfare weight, you know, in these different contexts, right? And how, you know, how much, or really more precisely, you can infer things about how much people's willingness to pay is actually telling you about their, you know, sort of their social value of the allocation, right? How much of it is true willingness to pay, you know, true value for the object versus being near your budget constraint or lower bargaining power or something. In all these contexts, the same sort of like using the market to identify people's types, you know, in welfare types, if you will, works well. And then there's lots more, both, you know, sort of papers that find sort of similar rationing dynamics using versions of the ironing technology, you know, or like, you know, sort of other contexts where we have these sorts of, you know, goods allocations with heterogeneous welfare concerns. And you know, we're hoping that, you know, that this is the start of, you know, sort of the start of our thinking about how to, you know, use markets with higher order welfare objectives rather than the end. And so to the last point in the last like minute and a half, let me just sort of list a bunch of other contexts and questions one might think about. I already mentioned the possibility of like, how does this work in a platform competition setting? You know, is there ever an incentive to implement redistributive allocation as a way of, you know, as an active, like, you know, profit maximizing strategy? In some joint work with Shengwu Li, we're thinking about queuing, you know, sort of like in this dynamic queue, a dynamic rationing paper I mentioned up here, you know, sort of trying to understand, you know, how you can use people's value for time as a way of, again, eliciting something about their relative need. And here we're thinking of like, what happens if people sort on value for money versus value for time? You can sort of use the queue to find some of these people potentially who are, high value for the good, but also high value for money. In the event, of course, that they have lower value for time, that's a way of sort of sorting them within the market. Also, everything we presented today has linearity assumptions, but of course, especially in cases where we're concerned about inequality, linearity is a really bad assumption, right? We're worried about income effects, we're worried about risk aversion. All of these things, like especially with low income or high risk populations, are first order. And so understanding like, how those types of additions affect the model in the optimal allocation. Sorry, now I'm losing my voice too. This tutorial is, it's a good thing the second half is a replay. Otherwise, like, you wouldn't be able to hear any of us. All of that said, right? So despite the linearities in our model, our instinct is that pretty much all of the dynamics we've described are going to carry over to a framework where there are general equilibrium effects. Just, you might see them, the magnitudes reduced, right? So for example, if we, if we think of the market allocation, receiving the good as affecting your welfare weight because now you have a house, say, like, it's housing allocation, that's a big part of people's income. By receiving public housing, now our welfare weight on you goes down because you've essentially just gotten this huge income shock. That will reduce the extent to which you want to do public housing on the margin, but it shouldn't eliminate it. It's just going to sort of compress down because people's, the welfare weight conditional on receiving the good is a little bit lower than what you would have thought before you received it. Also, everything we've done here is a very ex ante perspective, and we're using that very strongly. We're using this sort of like, continuum model and to sort of get that the algorithms are very simple, but we're also using the ex ante-ness to sort of, make the welfare calculation work out. But again, in the context with inequality, we're often concerned not about ex ante, but ex post. And so like figuring out like, how do you do redistributive allocation when what we really care about is, the ex post allocation, not sort of, people's ex ante opportunity, super first order. Again, I'm a couple minutes over time, so I'm not gonna talk for too much longer, but give me another minute just to say also, of course, like, we'd love to see sort of how this all feeds back into people's incentives to invest, right? If you know that the market economy is going to somehow improve equity, like if you're somebody now who's on the lower end of the income distribution or on the higher end, what does this do to your incentive to invest in things that might make being in the market more valuable? And then very, very central, we've sort of taken this pure market design approach, looking just at this individual market, but really what's interesting here and, for thinking about policy is how that interacts with conventional redistributive tools, right? Like you have taxation possibly with some friction and, the opportunity to redistribute through markets. As I hinted in the review, we think you might actually still sometimes want to use both, but understanding when and how these things really complement each other and when they substitute is really important if anyone wants to bring this stuff to practice, as are all of the practical limitations and implementation challenges that are way outside the scope of today, but we've been thinking about them some. So if you want to discuss, please let me know. All right. With that, sorry, we're 3 minutes over, but we will wrap up. Thank you so much for joining us. And as I said, we're all three of us and our extended collaborator network in this space are really excited about the potential of markets to improve equity rather than just efficiency. And we'd love to hear your thoughts about how that might work better. QED. Thanks so much.